We're live. You're being recorded. So I want you to write up here on today, after today's date, 3/7/22, what a polynomial is. Polynomial. Okay, write down. We're going to write the definition of a polynomial. Poly means many. It's just a Latin word for many. And nomial means number. When you have variables, variables are numbers, but we just don't know what numbers they are. That's why we call them variables. I'll say it again. Poly means many. Nomial means numbers. If we have many numbers, then a polynomial looks like that's a polynomial. That's a polynomial. Okay? That's a polynomial. That's a see many. That's a polynomial, and that's a polynomial. Okay? We want to look at their graphs, but polynomials are expressions with whole number exponents. Shh, Brian. Shh. Whole number exponents. So what is a whole number? I have it written down here. The whole numbers are these are 0, 1, 2, 3. These are whole numbers. So any exponent that is either a fraction or a decimal is not a whole number. So all of our polynomials are going to have exponents that are whole numbers. Like that's a whole number, right? If it's 0, 1, 2, 3, it's a whole number, okay? And they're curvy, aren't they? You guys saw that, right? They're curvy. So if I take a look at example 1, and if you want to put that on Desmos and graph it in, it looks like this. And you can put it on Desmos if you want to see what number 1 looks like. But it looks like this. It has a degree of 2 because of the exponent of 2. What Cassidy said was pretty good because anything with degree 2 can have 2 x-intercepts. It can. So degree 2 will have at most 2 exponents, okay? 2 x-intercepts. When I say at most, we could have had this rendition of it. Just watch, just watch, okay? If I had y equals x squared, it could have looked like this. If I had y equals x squared plus 4, it could look like this, okay? Don't write those down, just look. But it can have, at most, 2 x-intercepts. You see that? It's possible to have 1, it's possible to have none. But at most, 2 x-intercepts.
We should write this down?
No.
Oh.
Because that's coming. Because all that's coming, okay?
Oh,
but it doesn't mean it always has 2. Because you can see here it has 1, there's none. But it can have at most 2. It's second degree, okay? Right now. Does that make sense? Second degree, 2 x-intercepts. Nice job, Cassidy. Let's look at the second one. So these are called zeros for a couple of reasons. One reason is if I were to plug 2 into my equation, check it out. If I put 2 in my equation, 2, right? X equals 2, x equals negative 2. If I go 2 squared, subtract 4, I get an answer of 0. That's why we call them zeros. Or if I plugged in negative 2, I also get 0. They're called zeros because they are answers that make the value of y be 0. Also, it has a height of 0. Their x-intercepts are also called zeros. Okay? So any place it crosses the x-axis, we call them zeros, okay? They're also values that make the equation equal to 0, okay? It has a vertex, doesn't it? And the vertex is at 0, negative 4. We know that. And that's a minimum value. Isn't that a minimum value? So my minimum is at negative 4, because that's the lowest it goes down, right? So it's something new. We're in Algebra 2 now. We've moved beyond geometry. Example 2. So try example 2 on your Desmos, okay? It should look like this. Example 2 should look something like this. Go ahead and put it on Desmos and check it out. Okay. All right. Did you get it to look like this? All right. And what's the minimum and maximum values? Well, great question. I'm glad you saw that. A lot of kids don't. Okay. Now, we're going to rephrase this question because the maximum value goes out to infinity. Right? And the minimum value does also. So what we have here is what we call a local maximum and a local minimum. So it does have a local max and a local min, okay? So what it has is a local, yes, and a local min. So that's kind of our come back for a second. Hey, wrong word, bad word. I'm sorry. Bad word. Use good words, okay? So, hold on, let me clear these out of here. Interesting, it does f of x. Huh.
You can just press the little X's.
Oh, okay, thanks. I didn't know that. Okay, and come on, phone, squish for me. So, watch. This is what I love about Desmos, is tap. So my local max is at the point negative 1.7, about a 10.4. Write that down. I got that from my calculator. And my local min, just tap, is at a positive 1.7, negative 10.4. Okay, how's that? So far, so good? Really easy. I just tapped on my phone. I got my local max, local min. Now, where's the graph going uphill? Increasing. Where is it going up? Where is it increasing?
0, 1.1.
It's increasing at multiple spots.
All the way to here. Is it going uphill, right? And it's also going up here, right?
Yeah.
So it's going uphill. And let's talk, instead of increasing, let's talk about positive slope. So it has positive slope here, negative slope, positive slope here.
Oh wait, it's mirrored.
So we're going to say it is, yes. Sorry, right. So we're going to say it's increasing from negative infinity to negative 1.7. X values, right? Increasing X values. Okay, write that down. X values. Okay? Now, I want you to see how this works. A lot of kids get confused. Okay? All right? So, use a better word. Show me your intelligence.
It's really low. I'll pray for you.
What's the nugget?
What the nugget?
Use an intelligent word. So, think about this.
Well, this is the corner pray.
Guys. So, I'm way back here on the graph. And I'm way back here on the x-axis. I'm standing on the x-axis. Imagine this. I'm standing on the x-axis. Where's the graph? Where's the graph? Way out here, where's the graph? Way down there, right?
Yeah.
As I move forward on the graph, it's going uphill, right? The graph is going uphill. So as I move along, the graph is coming up, coming up, coming up, coming up, it's right there. So it's increasing from negative infinity to 1.7 along the x-axis. Does that make sense?
And then it's decreasing from negative 1.7 to.
And then it increases.
So 1.7 to negative.
Yes and yes. Let's write that down. Well done. So it is also, then it's decreasing from negative 1.7 to a positive 1.7, right? Now it's also increasing one other place. It's also increasing from
1.7
to infinity. So it's also increasing from here. It's still, as I move along the x-axis, it's going up.
Wait,
Agreed?
why is it increasing from negative?
So from here
Oh, never mind.
to here, it's going downhill. Negative slope. But it's also then increasing from positive 1.7 to positive infinity. All right, thumbs up. Good. Let's turn the page. I'll wait for you. So it's always the x values. X values. What x, listen carefully, what x values make it go uphill? What x values make it increase? What x values make it decrease? What x values make, I don't care about y values, what x values make the y values get big? What x values make the y value get small? See what I'm saying? What x values? Okay, turn the page. Okay, now, let's sketch this one. Okay, so if I sketch this one, you can put it on the phone. Try this one. Madison, here you go. That one on the phone. There you go. Okay, put this one in Desmos. Should look like this. Did you get a picture that looks like this? You hang on to that. That is very good. It does. It really does. It really does. Hang on to that, because it is in mathematical theory, 3 answers. Which happens 3 times in the same spot. Hang on to that, okay? You're way ahead of the class. Okay? Now, is there a max? Is there a max or is there a min?
There's slowly going up.
This is called an inflection point. And in business, we talk about inflection points. This is also a parent function, yes. This is called an inflection point.
We write that down.
Yep, it's neither max nor min. It's called an inflection point. Yes, it's at the origin. Good word. That was a great word.
What are your smart words, Pat?
Nuggets.
I have so much shit to do. I cannot vlog, live
Okay, concave down.
Oh, the little guy.
Watch. This concave. Concave down. So if I were to keep going, it kind of concaves down, and then all of a sudden it goes to concave up. Do you see the illustration? Concave up, concave down?
Yeah.
Concave. Now listen. In business, this is important. You'll hear it in the news. They'll talk about inflection points in businesses. And so what happens, I'll give you an example. Let's say we own a business, and you put me in charge, right? And then all of a sudden, we're right about here, and we're not making as much money. It doesn't look like we're looking good. Then you fire me, and you bring in, say, Michael. And then all of a sudden, Michael changes the business, and it takes off again. In business, they talk about that as an inflection point. It's an important thing in business, isn't it? If you have an inflection point in business, it means you turn something around, either for the good or for the bad, right? It's neither a max nor a min, okay? Where is it increasing? Everywhere. Everywhere. So it increases, increasing,
Was it still going up?
yes,
Oh.
increasing from negative infinity to positive infinity, okay? Okay, let's look at number 4. Okay, let's graph number 4. Yeah, but we have a decimal sign. All right, let's take a look at number 4. X to the 4th. Look at this back. Subtract 3x squared. Oops.
Oh my god.
I have a broken wheel.
Plus 2 minus 5. Okay, there it is. All right, looks like this. So, looks something like this. Okay, take a look. This is it. All right. Yeah. Right. Right. So what Cassidy said was correct. This graph crosses here, but if I change the y-intercept, it would have gone up and come back down. So it could have crossed in 4 places. Could have.
So basically,
But it did.
the exponent, that's the max number.
Oh my gosh, you are so on top of this. That is the maximum number of what we call real zeros.
Oh, okay.
Okay?
Oh, okay.
Right? Real ones. Where it crosses. It could cross at most 4 places, right?
Yeah.
Okay, now,
Oh, wait.
does it have a local max? Local max? Does it have a local max?
Yes.
Right there. Its local max is here at 0, negative 5. Okay? Does it have a local min? Does it have a local min? Sure, but we just have to find it, so we use Desmos. And I tap. Okay, there's my local mins. So my one local min is at a negative 1.2 and negative 7.25. And I have another local min at a positive 1.2 and a negative 7.25, okay? Okay. Now, number 5. We're going to graph number 5 and talk about n. Yes, I can. Yeah, I sure can. X to the 5th. Sophie, I'm just going to graph this next one, but I'll wait for you, okay? Okay, cubed.
Wouldn't that?
Okay, there you go. This one's really weird because I'll zoom in, right? This one has a max, it has a min, it has an inflection point, doesn't it? Has a maximum, has a minimum,
I don't like that one.
right? So I'll zoom it in a little bit so you can see it. Okay, right? So it looks like this. Doesn't have to be perfect.
For free, I'm your homie.
God, I wish you would stop this. Oh, my.
So, this one has a max, a local max. It has a local min. It It has Juan, will you go out the hall? Please, go in the hallway. I don't want to hear it again. Go in the hall.
Go to the hall.
Yes, go sit in the hall. I don't want to hear that word again.
Let's go pray one. Let's go pray. Let's
Go in
go
the
pray.
hall.
Let's
I don't want to hear that word
go
again.
pray. Go pray. Go pray.
Don't want to hear that word again.
I triggered it.
You're getting so.
And Juan, we are on film. You are being filmed.
Oh wait, I gotta pray for the.
And it has 1, 2, 3 zeros. Okay, write that down. Has a local max, has a local min, has an inflection point, and it has 3 zeros. Okay? It could have more, but it has 3. Now, end behavior. As x approaches infinity. Okay, this is important.
How
Why?
can you approach infinity?
You can't get there, that's why we say approach. So you can't get to infinity, but you can approach it. You get bigger and bigger and bigger and bigger and bigger and bigger, right? So as x approaches infinity, what's y doing? What's the graph doing? What's the graph doing?
It's increasing.
So the y is going to infinity also. End behavior is like what's happening in the end. So Michael's right, you can't get to infinity. It's impossible. Infinity is not a number. But what you do instead of getting to infinity is you approach infinity. So as x gets bigger and bigger and bigger, the y value gets bigger and bigger. So end behavior as x, this is approaches, this little arrow means approaches infinity. Y approaches infinity. Does that make sense?
Because we're walking with it too.
So end behavior as x approaches infinity, y approaches infinity. Now on this side, as x approaches negative infinity, what's y doing? What's y doing?
Decrease.
And it's heading towards negative infinity. So we're going to say y approaches negative infinity. Okay? So today I have a little assignment for you. We have time to get it done. I want you page 63. I want you 1 to 13 all. Okay, and I'm going to talk to Juan. I'll be back.
I prayed for him.
He is still a wonderful young man. We just got to clean up his mouth.
I prayed for him and I sent him a link. So
Okay.
he's good to go.